I want to tell you about something that bothered me for years. Something so small that, strictly speaking, no one has ever seen it. Let me ask you a question. What do you think happens if I keep zooming in on space? Closer and closer and closer still. Most people think space is like a smooth sheet of paper. You zoom in and it's still smooth. I used to think that too. After all, that's how geometry works. That's how physics worked for centuries. But then I discovered something unsettling. At a certain scale, an absurdly tiny scale, the idea of space itself begins to fail. Not bend, not curve, fail. And the reason this mattered to me is simple. Every law I trusted, quantum mechanics, relativity, energy, time, started talking over each other. They couldn't all be right. So today I want to take you with me. Not to an answer, because we don't quite have one, but to the edge where physics stops making sense and starts becoming something else entirely. Let me show you how I got there. When I was a young man learning physics, we believed something very comforting. Nature could always be examined more closely. You take a ruler, and if it's not precise enough, you make a better one. You take a microscope, and if it's too weak, you build a stronger one. That idea goes all the way back to Newton. Space was a stage, time was a clock. Things happened on space and in time. Then along came Einstein and he ruined the party in a beautiful way. When I first really understood general relativity, I felt like a magician had pulled the floor out from under me. Space and time weren't just a backdrop anymore. They moved, they stretched. How to bend and space told matter how to move. Marvelous, elegant, deeply disturbing. But here's the problem I couldn't shake. Quantum mechanics was also true. And quantum mechanics does not care how uncomfortable you are. In quantum theory, the act of measuring something disturbs it. Energy fluctuates. Particles appear and disappear. Certainty evaporates. So I asked myself something simple and very dangerous. What happens if I try to measure space itself using quantum mechanics? No textbook gave me an answer I liked, because to measure something very small, you need a lot of energy. And energy, according to Einstein, has gravity. That's when I noticed something in my calculations that made me stop. If I tried to probe space at an absurdly small distance, I might create a black hole. That's not a metaphor. That's a calculation. And suddenly physics wasn't just hard, it was contradicting itself. Let me tell you where this gets interesting. So I did what I always did when things stopped making sense. I played. I imagined a tiny experiment, just a thought experiment, no grant money required. Suppose I want to measure a distance delta x. I shine light at it. Shorter wavelength light gives better resolution. That's basic physics. But shorter wavelength means higher energy. And here's the catch. At some point, the energy needed to see that distance become so concentrated that space-time collapses. Boom! Black hole, end of experiment. So there's a limit, not technological, not practical, but fundamental. I didn't invent this limit alone. Other physicists noticed it too. But when I personally stared at it long enough, it felt like nature was whispering something. Stop asking this question in this way. That scale, the distance where this breakdown happens, is what we now call the Planck length. About 10 minus 35, 10 minus 35 meters. I want you to appreciate how ridiculous that number is. If an atom were the size of the observable universe, the Planck length would still be a speck you'd have trouble pointing to. And yet, that speck may be the smallest meaningful distance there is. At first, I didn't like that idea at all, because physics to me is about describing motion, paths, changes, processes, and the Planck length threatened all of that. I remember the moment I realized this wasn't just a calculation error. I began asking a more radical question. What if space isn't smooth at all? What if, at the smallest scale, it's more like a quantum object, fuzzy, jittery, uncertain? I used to tell my students, don't imagine atoms as little billiard balls. The picture will betray you. Now I'd had to apply the same lesson to space itself. Some physicists imagine space-time as a foam, tiny bubbles forming and collapsing. Others imagine loops or networks or vibrating strings. I didn't care which picture was right. What bothered me was something deeper. All of our pictures depended on space already existing. But what if space emerges? I remember arguing late into the night with colleagues. Some convinced gravity must be quantized like everything else. Others convinced we were missing the point entirely. and then something unexpected happened. But then something unexpected happened. I realized that every attempt to describe the Planck scale used concepts borrowed from the large-scale world. Distance, time, geometry. We were trying to describe the foundation of language using the language it creates. That's like trying to define a word using only the letters it contains. No wonder it felt impossible. This is where my understanding completely shifted. I stopped asking, what does space look like at the Planck length? And instead I asked, what operations are even possible there? In quantum mechanics, we don't ask where a particle is. We ask what can be measured. So maybe space-time itself is not a thing, but a set of relationships. I began to suspect something heretical, that the Planck length is not a place. It's a limit on meaning. Below it, the question of where stops making sense. Think about temperature. You can always ask how hot something is until you reach absolute zero. Below that, temperature isn't in negative cold. It's undefined. The Planck length felt like that, a boundary where geometry gives up. And here's what really shook me. Time might break down too. If space is uncertain, then so is time. Cause and effect blur. The very idea of a before and after starts to wobble. I had spent my life teaching that physics doesn't need certainty, it needs consistency. And here, consistency was cracking. Here's what changed everything for me. I noticed that every physical theory we trust is silent about what happens below its own limits. Newton can't handle light speed. Relativity can handle quantum uncertainty. Quantum mechanics can't handle gravity. Nature isn't obligated to give us a continuous zoom feature. Maybe reality is like a digital image. Zoom in far enough and pixels appear, not because they're fundamental objects, but because resolution itself has a limit. Or maybe it's not even that. Maybe it's simply the scale where our questions stop being well-formed. Everything I thought I knew about it, what happens, it was about to change. And then it hit me. The Planck length is not telling us what space is made of. It's telling us what space is not. It is not infinitely divisible. It is not a passive stage. It is not something you can interrogate without consequence. At that scale, energy, geometry, and information become inseparable. Trying to observe space-time creates space-time effects. That's not a bug. That's not a bug. That's the universe protecting its own consistency. When I finally accepted that, I felt something familiar. Not certainty, wonder. The same feeling I had the first time quantum mechanics worked, even though it made no sense. We are not standing on solid ground. We are floating on equations that work astonishingly well until they don't. And that edge, that trembling boundary at the Planck length is where the next revolution will come from. I want to ask you something that sounds innocent, but once it bothered me, it never let go. What time is it? Really? Not what your watch says, not what your phone says. I mean, what is time itself? Most people think time is obvious. It flows, it moves forward. One thing happens, then another. I used to think that too. After all, every equation I learned had a little t in it. But then I noticed something disturbing. When I looked carefully at the laws of physics, the real ones, time didn't seem to be doing anything at all. And that scared me, because if time isn't fundamental, then what does before even mean? What does after mean? What does change mean? Let me tell you how I stumbled into that problem, and why I still don't sleep quite the same way afterward. When I was learning physics, time was the most reliable thing in the room. Clocks ticked, pendulums swung, planets moved along neat trajectories. Even when everything else was confusing, time was there, marching forward, minding its own business. Newton treated time like a God-given backdrop. It existed whether anything happened or not. Then Einstein came along and once again spoiled our comfort in the most elegant way possible. Suddenly, time slowed down. It bent. It depended on motion and gravity. I remember the first time I really felt that idea, not just understood it mathematically. I thought, all right, time is flexible. Strange, but manageable. But here's the thing. Even in relativity, time still exists. It just behaves badly. What really bothered me came later, when I stared too long at quantum mechanics. In quantum theory, we talk about probabilities changing in time. But the equations themselves, they don't care which way time flows. Run them forward, run them backward. They work just fine. That should have made me uneasy sooner than it did. Because if the laws don't know which way time goes, why do we? Let me tell you where this gets interesting. I started with a simple question. my favorite kind. Where does the now come from? Physics lets me calculate yesterday and tomorrow with equal ease. There's no special symbol for this moment. No equation points at now and says, here it is. So I tried to find it experimentally. Take a film of particles bouncing around. Play it forward. It looks normal. Play it backward. Sometimes it looks normal too. That annoyed me, because my experience of time is nothing like that. I remember the past, not the future. Eggs break, they don't break. People age, they don't unage. So I thought maybe the arrow of time comes from disorder. Entropy. That's what we tell students. That's what I told students. But the deeper I looked, the less satisfied I became. Entropy explains why we remember the past, but it doesn't explain why the fundamental laws don't. I remember the moment I realized this was more serious than I thought. I was staring at equations that worked perfectly, and yet said nothing about the passage of time I was living inside. That's a dangerous feeling for a physicist. So I tried something else. I asked myself, what if time isn't something that flows? What if it's something we infer? In quantum mechanics, nothing happens unless it interacts. No event, no event, no event, no time marker. That made me uncomfortable because it suggested that time might be more like temperature, a collective concept, not something built into the universe at the smallest scale. I remember long conversations with colleagues who insisted time had to be fundamental. Otherwise, they said, how do things change? And that's when I noticed the trap. We were assuming time to explain change, while using change to explain time. A perfect little circle. But then something unexpected happened. I realized that many equations of physics don't describe evolution in time. They describe relationships between events. Time was just the bookkeeping tool we used to keep track of them. This is where my understanding completely shifted. I began to imagine a universe where nothing moves at all. Instead, the universe simply is a giant, self-consistent pattern. What we call the present is just where our consciousness happens to be embedded in that pattern. That idea made my skin crawl, because it means the future might exist as much as the past. Not predetermined in a simple sense, but real. I didn't like that. I still don't. But physics isn't about liking answers. I asked myself, if time doesn't exist fundamentally, then why does it feel so real? And the answer that kept coming back was, because memory exists. We are systems that record information asymmetrically. We leave traces behind us, and we call that direction and time.